theory plus mathematics actually. It's not only theory actually. So everything is related. So let me show you that what we did yesterday actually. I hope you can see that,
Yes, sir.
Yes, sir.
right? So this is, I'm just showing my, I don't know whether you can understand my handwriting or not, but I hope it's somewhat, uh, let me zoom it actually, that would be much more better. Yeah, yeah, you can see that. So we were actually were trying to do the means this momentum balance, right, in rectilinear coordinates. So first we are doing the rectilinear coordinate, and later on we will do for cylindrical coordinate. So this is what you already know, that force is the rate of change of momentum. Actually, the linear momentum change is called force actually. So that's what you have here. So P is actually the linear momentum. The linear momentum can be calculated velocity into mass, and if you have several particles, or let's say differential mass of differential volume, so you individually packets of that, all packets corresponding velocity, keep on multiplying and adding, you will get total momentum of the system actually. Now again, the force is, as is also being told to you, taught to us actually in the beginning, mass into acceleration only. So therefore, you have here that df equal to dm dv upon dt. So this dv upon dt is actually is your acceleration actually. So total acceleration of fluid particles. So the small d we have converted to the capital D, because that we have converted into the material derivative or substantial derivative or total derivative. Based on that, you got, this is the acceleration of the particle. If you have velocity vectors, so you have x component of velocity, y component, z component, and a disturbance due to unsteady state characteristics, that is del v upon del t, last term, that is called local acceleration. So this is the means another expression for force. So you have two x. So one have force from this side, another one is from that side actually, that dp upon dt. Now, this I have shown to you already, that we have taken a differential volume of this dimension dx, dz, and dy. And at the center, as I told that these are the surfaces. So these surfaces will have will bear the forces. Either may be parallel to the surface or maybe perpendicular to the surface. No matter what direction you are applying force from outside. Let's say you are applying force inclined, so it will give two components, one is parallel to the surface, one is the normal to the surface. If you are directly applying perpendicular to that, it means you are just having a compressive force. If you are just pulling it, then you have a means expansion force. So if you are just parallel, you have a shear force. So all the time is being applied at the surface. So for this derivation, what we did, the stresses at the center, we consider the sigma xx, say tau yx and tau zx. That's what we have the mention here, because first we want to do what is the net force in only in x directions, because we don't want to put all three in one side, because then the number of variables would become too much and it will become very hard to understand in the beginning actually. So that's what we have taken in that side at the center, this one, the sigma xx, because wherever your see in this case, this if you are talking about this this actually your right side. So here perpendicular is going to x side, and direction of force is also going to x side. So both are xx. Your plane and direction both are xx. So therefore it has converted to the sigma, because that will give the normal stress. So normal stress would be either normal stress is just called pressure only. So that's what is being changed to sigma only. Rest of the surfaces, this side, direction is this, but plane is y. So you will get shear only. Okay, so that's where you have all other surfaces would have shear forces. Only this x plane would have the normal forces only. That's what those x side one being converted to the sigma only. So this I explained to you, and then we wrote all these down. The normal stress on left side, so y Taylor's means expansion, and then you have the right side one, and then you have a top side, top on y means top plane. So you have plane is y, direction is x. Therefore, the first is plane, next is direction there. So next part is direction always. So this is what you have to define your nomenclature. Not you cannot write anyway y, x, z, x. No. First is always plane, second one is direction only. Same thing, bottom one you wrote here, then you wrote actually the front one, front is front to this monitor, and a back one. So you wrote all of them. Then finally you have added all surface forces in x direction there. So you added all surface forces left, right, top, bottom, front, and back. So you added all of them, and based on that, you got this equation that all the surface forces is the sigma xx and del sigma xx upon del x, delta yx upon del y, delta zx upon del z, dx dy dz. So that's what you got in the last class. After that, because you want to calculate net force, so this is the surface force. The every system would have its own body weight. So body weight, as we know, it acts always in downward, but we don't know what our orientation is body is. Let's say body is inclined, so body weight is this side. So some component would be in x side, some component would be in y side, maybe in that side. So you will have some component z side also. So body multiplied by, let's say, cos theta sin theta will give you the corresponding component in x, y, z direction. So therefore, if you want to calculate net force in direction x, so it would be a net force in direction x by body weight plus net force by surface forces in direction x. So therefore, you got two component, dbx and dfx. So dbx is just from body weight. So body weight is just mass, so density, this is the volume actually, dx dy by dz, and into gx, so component of g in that particular direction. So this is the body weight component direction x, and these are all the surface forces. So you add them up, you got now the total force. Now you balance from your previous one. So same thing can be done for y direction. So for y direction में क्या होगा, जो आपका last coordinate है, this last coordinate, here you have xx now. So this the last coordinate, you just change it by y only. Everything would change automatically to y coordinate only, means y direction force balance. So here you change this y, this also would be changed to y, this also would be changed. So your second x would be changed by y only. So you will get for same thing for y direction forces. Similarly, you can, so y direction, if you will do the balance, you will get this one, y direction, the surface force. Same way you can do for surface force in z direction. So it will complete your, all your x, y, z. Okay.
Yes,
So
sir.
now this is your means expanded picture of your control volume. Okay, सारी surfaces को आपने अलग कर दिया दूर से. So this is how it will look like. So this is your actually your right side one. So right side, it has the if you are balancing the force means the stress in direction x, it is becoming the sigma. If you are finding in y direction, it will become tau xy. If you are doing in z direction, it will become tau xz. So now is plane pe you have all three. You have component in x direction, you have in y direction, z direction. These are the three components at each plane. So here plane is x. X is the plane because perpendicular is going to direction x. But directions are now three. If you are doing x balance, you have the sigma xx. If you are doing y balance, you have tau xy. If you are doing z balance, you have tau xz. So these are the three stresses at one particular plane. Same thing you will get on this right side one. The right side one also you will get the same thing. Okay. Then you will get on top side, same thing again, top side also you will have three components. One is in y direction, one is in x direction, one is in z directions. Okay.
Yes, sir.
Fine. So that way you are the defining your the direction. Now you would come to know how this thing has burnt down. ये वाला नीचे क्यों चला गया? You might have the notices ना कि यहाँ पे ये वाला this tau y x is up. Now here tau y x is down. Can you tell me why? Why is it so? Directions actually you would be calculated by a long time back, as I told you previously. Directions need to be calculated by two things. One is your magnitude of shear stress, which you are going to calculate, which is that tau you are calculating mu dv upon d or du upon dy, right? That's what the Newton's law of the mean the viscosity. Yes or no?
Yes, sir.
Right. So calculate two things. One is its magnitude. One is its direction, right? Direction of the plane or motion. So direction of plane actually. Once you have directions and magnitude both are having same sign, your magnitude the total direction would be plus. If magnitude and directions are different, then it will become minus. That's where you are finalizing it. So you can think it, then you will come to know what is happening in that particular part. So these are all 6 surfaces. Every surface would have 3 components. So total are how many components? Total are how many?
18.
18. So 18 may some are overlapping. Sigma xx, tau xz. So total it will become half of that, 9 actually. So 9 by 9 stress tensor बन जाएगा ये 9 by 9 matrix actually. Okay, so that I am not confusing you by the tensor term. So just leave the tensor. So once you did X balance, so you did a body weight, you did a surface force. So this part is being done in the last class here. So you got this. So now we will start again for that part again. Now same thing for Y component, you will get same thing for Z component. So this you got in terms of the means the stresses. This is your force balance in direction. Now question is that we cannot measure the stresses in any fluid easily because there are no simplified technique to that. We can measure but not a simplified techniques. So our idea as an engineer or all other thing, we want to convert every formulation in a simplified way where we can do the direct measurement. So these stresses, we want to convert it in terms of velocity because velocity is the only thing which we have the several techniques to measure them much more accurately actually. So therefore the stresses we are converting to other measurable property. So what you have here first, that this is your force mass into acceleration. So you wrote the acceleration in terms of velocity. This is your left side. Right side you have this one. This I want to show that from where this is coming. So right side you have these components, right? The rho gx sigma del x upon sigma del sigma xx upon del x, delta yx upon del y. This I want to show that how would it be calculated to you, because this part you already know from here, from backside. Only thing this sigma xx, tau by x, tau zx, we were doing last class, and some of you had tried. So only question is that from where the sigma came. Tau by x is being explained to you based on your Newton's law of viscosity. So there was no confusion in that. So Newton's law of the viscosity, let's say you are talking about one-dimensional flow. So your Newton's law of the viscosity is given by this only, that tau by x is equal to du upon dy. This is only for one-dimensional. Now it is for three-dimensional planes. So every time you have two planes, x or y or z or x. So you will have two stresses in that. So therefore, your tau yx or tau xy would be given by this mu del v upon del x or del u upon del y. Okay. So this is the net stress of tau xy or yx in x by plane. Same thing for z by plane, same thing for zx plane. Now this, I gave you this one. So this is the normal, actually means the stresses need to be calculated from here, the thermodynamic pressure. This is
सर
from this.
सर इस shear stress वाले फॉर्मूले में
हाँ,
opposite coordinate क्यों आया है डिनोमिनेटर में जैसे del
uh,
u
yeah. So if you are moving in this side, so you want to calculate the shear stress. So shear would be applied on a surface. So if you want to move this side, your plane is y. Yes or no?
yes sir
Right? So if you want to move upside, your plane is x. So therefore, your velocity will change with respect to x coordinate, not in terms of y coordinate. If you are moving this side, you are moving in this side. So if you have the surface is only this side. So this surface would have the shear only, not this surface. So
okay sir
okay, so the your velocity or the stresses would be on the plane. So if you want to move in this side, so your plane is x. If you want to move in this side, your plane is y, because you are the moving on y plane, right? So that way your this coordinate comes in that way, your the direction and the another coordinate which is perpendicular to the motion only. Fine.
yes sir
Okay. Now there was a question here that from where this came. So I am just trying to explain if I can explain you well. So this explanation of these terms, you have this, you have the thermodynamic pressure here. So this is being calculated based on density and the temperature, and then you have your gas laws for that. Your the calculation equation of the state, van der Waals equations and Planck-Robinson equations. Those will be taught to you in the thermodynamics actually. Now, suppose this is true, whatever is the mention here. Based on that, we were trying to drive it first. So let's drive it first. So at the place of the sigma, we have put that value here. At the place of this, this is what term here, tau yx. So you have put here. You have here tau zx. So you have the substituted here. So I asked you to drive it. I was also trying to drive it in that particular class. So if you will substitute here and do it here, you will get in this particular term. You have just arranged the term in that particular way. So this equation at this particular time is called Navier-Stokes equation actually. At this particular time, all these one. Okay, these are called momentum equations, and in short, these are called Navier-Stokes equations. This was the name of the scientists. They drive it actually. After that, we want to calculate what this term is, del dot v vectors. So I want to explain you this, that how this term will be calculated there. So we wrote again the constant here for incompressible flow with constant viscosity. We have put a constraint that incompressible means density is constant, So we want to do the change in previous one, a big constant viscosity also. So in previous one, what you have here, so this viscosity will come out outside the differential sign. You talking about incompressible flow. So from incompressible flow, you have the continuity. So this term will come from continuity. Your del dot V term would come equal to 0. So do you remember the continuity?
Yes, sir.
So in that case, for the incompressible fluid, that comes del dot V equal to 0. So this term will get cancelled. Viscosity term from all these terms will come out outside of the differential sign. Then we can rearrange all of them, and finally you will end up with this equation actually, that mu del square u upon del x square plus del square u upon del y square and del square u upon del z. This is for your momentum balance in direction x. Okay, this is your momentum balance in direction x only. Same way you can write for direction y, for direction z. Now this is your continuity, right? This is your continuity in the rectilinear coordinate we derived long time back, that del rho upon del t, rho del u upon the del x, rho del v upon del y, rho del w upon del z. We derived it in previously, the continuity in a differential coordinate, right? Now, if you want to change it for incompressible fluid, it means density is constant, so your first term will get cancelled. Density will come out from here, so you will finally end up a term del u upon del x plus del v upon del y plus del w upon del z equal to 0. Now, all del can be converted into the del operator, so you will get finally a del dot vector b from here. Okay?
Yes, sir.
So similarly, this part I will show you the later. Actually, the derivation in the cylindrical coordinates. So I just want to show you that the thermodynamic, the pressure thing. So finally, you will end up with this was the thing I was talking to you just now. For constant density fluid, you will get this. So you take the del common. So finally, you will end up this, and this term can be represented by del dot vector b equal to 0 in terms of mathematics. Now we were talking this, so I will ask you also if you can have the access to this book, that Analysis of Transport Phenomena by William M. Dean. So this gives the derivation of the sigma actually. So in this, sigma is being actually defined by two terms here, that P into I plus tau. Tau is the shear, viscous shear stress, and P is your thermodynamic one, pressure. And then if you add that is called your total stress actually at a particular plane or a particular point. Now, how this sigma is being calculated? Again, sigma is equal to Pi for a static fluid, because the static fluid you don't have shear force component, right? So your tau will vanish there. Okay. So now you have there a derivative term at that particular place. So you are putting del dot here, the sigma. So you just put del here also. In previous slide you have a tau. You have also put here del upon tau again. So you got del sigma equal to del p plus del dot tau. So finally, you can change your continuity equations from this way, that your force balance equal to rho dv upon dt equal to. So this is the another way to represent actually your momentum balance. So I will end the momentum balance on x plane here. So further, if you want to read that particular term, sigma thing, you can read that one. And so far also I don't understand much from there, so you can also try it. So again, this tau is being calculated by this 2 mu upon the sigma for the Newtonian fluid. This expression is also given in that particular textbook. Now, what is this this is called actually, this is total, means the stress here. So this you have del dot B again B dot transport of that. So this again you can put here, and that time you got the term here 1/3 here. So this is totally from mathematics. So you just try to drive it if you can do it. कुछ हो सकता है?
ओ सर समझ में आया।
Yeah, मेरे भी समझ में नहीं आया अब तक actually. I always try to understand it. So still I will try actually today. I will again go through it once actually. So means the again you will have this from here 1/3 came actually here. This is the another scientist, a bachelor here in his PhD thesis. He derived that P, the normal stress, is always 1/3 of total stress is presented on all three planes actually, and then they end up with this particular formulation. The normal stress finally is given by this minus P 2 mu del U upon del X K minus 2/3 mu again del dot B actually. So we will end this part here actually. So this is what I have taken here. This K is the dilation viscosity. This term is local rate of the deformation of the fluid, and that is the identity tensor. So vectors and tensor I don't teach in the UG curriculum actually. So you can probably leave this term here actually. So I will come back to the our class part here. So finally we have derived this one. Okay. So with this means the yesterday's class and today's class, finally we have derived a Navier-Stokes equations for a differential element, and in for a fluid which is incompressible or incompressible fluid. Okay. Newtonian fluid. Newtonian means viscosity is constant. You have also put one more constant, incompressible fluid, and this is these are your momentum balance equations for XYZ coordinates. Fine.
Yes, sir.
Now let's see what are the applications of these. That's the next important part. Why we drive it? What are the use of that? Now, if you want to change this, let's say you have an ideal fluid. So what will happen in case of ideal fluid? Or ideal fluid, or let's say inviscid fluid. Inviscid fluid, what would be the property? Viscosity would be nearly equal to 0 only. So this term, that mu term in all these three will get cancelled. So you will end up with this one. This one you will end up this, so you will get rho del U upon del T, U del U upon del X, V del U upon del Y, W del U upon del Z equal to minus del P upon del X plus rho Gx. So these are called Euler equations. So Euler equations means this is again your momentum equations, but for incompressible inviscid flow. You have added one more term in the previous one. Inviscid flow means viscosity tends to 0. So you don't have any viscous dissipation term. Now, if I change something here further, if I make it steady state, what will happen in that case? If I just make one more term steady state, this term will get cancelled. First one.
Yes, sir.
Yes, sir.
Yes. So first term will get cancelled. So I will have with term here U del U upon del X, B del U upon del Y, W del U upon del Z equal to minus del P upon del X plus rho Gx. Suppose I want to make further constraint on that. Let's say I'm talking about one-dimensional flow only in X direction. So what will happen in X direction flow?
dw is 0 then.
X direction, let's say I'm talking about X direction flow and let's say fully developed flow. Fully developed flow in direction X over a Y plane. Over a plane Y, flow in this side, fully developed. Fully developed means if you move from here to here, either you calculate velocity here or here or here or here, it's not getting changed. That's called a definition of fully developed flow. So from this, actually your few terms will get cancelled. If you are talking about X direction, your this del U upon the del X term will get cancelled because you are talking a term fully developed flow. Velocity will not change in this side. That also you have a constraint from your streamline flow. What does it say? 1 minute. Huh? So streamline, what does it say? Streamline कुछ कहता है? Hello? Hello?
Yes, sir.
Streamline. Streamline say that what did you say?
Sir, velocity
चलो
vector
नहीं आएगा. Velocity vector
So
is
linear flow.
tangential to the direction of the flow, right? That is one thing. How does it change? That is not being taught to you that time. How the velocity changes. The tangential आपको बताया, that's fine. Let's do from here. Now, I will show you with the help of figure only. Let's say you have this. We want to drive it Bernoulli equation. So Bernoulli equation, what do? You take a streamline. Yes or no? That's what you have
Yes,
here.
sir.
So this is the means that this blue line is the streamline, is going in this side. Now out of that, we have just taken a differential section of that of length ds. Is पूरे streamline, we have taken a section of ds length. This is this one. Now this also we have considered, we have taken some thickness of that particular the streamline actually, or of that area of that is, let's say dA. Area of this is dA this side. So what you have here, so you have two surfaces. One is this end, one is that end, which will have some pressure there. So let's say at this particular point, you have pressure is P, area is dA, so you got a pressure force here. Now this surface again would have the pressure, so you have P plus dP, and the area is again same dA. So these are the pressure force on both the surfaces, one is this side, one is that side. Now this particular the streamline which you have taken of length ds, area dA, would have some its weight also, which is W here, which will act at the center only. So W is the weight of this particular stream tube कह सकते हो for timing, stream tube or the line action. This weight will act W. Let's say its inclination from vertical, the axis, the change in theta is this. Okay, so and your direction is taken in this side here. So you have here, this is your x coordinate and this is your z coordinate we have taken. There, okay. Here everything is fine. That we are just doing only x, y, z, and where these components are acting. Is this fine? Everything here? Till here.
Yes,
Let's
sir.
see what I have next. We want to do the force balance in direction of flow. Fine. We want to do the force balance in direction of flow. So force balance is dF. We are talking about the differential mass into acceleration. That is your force balance. Correct or not?
Yes, sir. Correct.
Yes, sir.
right? Now you have force balance, you have this side pressure, उस side से भी कुछ pressure आ रहा है, so this side pressure PdA, that side pressure this side, so you have minus of that, P into plus dP into dA. Body weight always acts downward, W, and its component is going to this side, cos 90 minus theta. Now you want to balance it to in the direction of flows, therefore you put a minus sign here, minus W cos 90 minus theta. Is this fine? This is the body weight. Should be balanced by mass into acceleration. So dm, acceleration is called dv upon dt only. Is that fine?
Yes, sir.
Fine.
Yes, sir.
Simplify it. So simplify it. If you will do that, you will get the next line here. And from here at the place of dB, I just converted this into this form. dB upon ds multiplied by ds upon dt. I can do this way. यहाँ तो कोई दिक्कत नहीं है. This is just a mathematics. Okay,
Yes,
I
sir.
did this way. Now, at this place, at ds upon dt, distance upon time is called what? Velocity only.
Yes, sir.
So I just got the another line here that minus dp dA minus w sin theta dm v into dv upon ds. Now, what is my sin theta? From the previous figure, I will get dz upon ds from here, sin theta from here, dz upon, this is your ds, right? ये वाला आपका ds है. So I will get sin theta. dm, I want differential mass. So I have the area, I have the length. So ds into dA is the volume, multiply by density is my mass, dm. Multiply by g would provide me the dw. So I have the everything, whatever I need to be the substituted in this equation, right? Correct?
Yes, sir.
So if I substitute that back here, so I am getting this equation. Now I am dividing this by ds and dA. So if I divide it, I am getting this equation, rearrange it. So I am getting v dB upon ds 2b upon this. I just put a factor of 2 here, and then dB upon ds, and finally I will end up with this 1 by 2 dv square upon ds. I can do that way. Here I
Yes.
have v dB upon ds. I just multiply 2 up and down, and then I got here 2b. So 2b I can get if I have inside the bracket b square term, right? So I got this, the half dB square upon ds. Now from 3 and 4, substitute them. I'm getting this equation now, minus dP upon ds minus rho g dz upon ds and rho dP square upon ds. So everywhere you have ds. Yes or no?
Yes, sir.
Now integrate for the streamline, integrate along the streamline. So if I put the integration sign over the entire term, and I am integrating along the streamline. So my total length of the streamline was just ds only. So I just multiply everywhere ds here also ds, here also ds. So if I do that, I am getting this, and finally I am ending with this minus p minus rho gz rho b square upon 2g plus a constant. So this is what your Bernoulli equation is. Okay. So
Yes, sir.
this is the one of the derivation of your Bernoulli equation. Let's say another thing. What else can be done for derivation? What Bernoulli constraint we did? You already know the sum of the constraint, because Bernoulli is the thing which is most frequently being used in fluid mechanics, where you have the motion of the fluid. No matter how genius, how expert a teacher or professor, researcher, everybody is, initial calculation everybody is doing from Bernoulli only, because this will give the idea what should be my value in in a most general case, because I am neglecting everything, I'm just talking about the ideal way. So this is the first starting calculation. Then we put some further complication and all this just to go close to reality actually. So maximum focus is always given on Bernoulli application actually. What are the constraints we have? We have put a constant here, steady flow first, incompressible, frictionless flow, flow along the streamline. These are the constraints we have put all these here actually. Now it is applicable on siphon. The siphon you might have seen a round pipe जो आप कहीं भी turn कर सकते हैं. It's a round pipe actually. Siphon you might have seen. I hope Punjab में I have not seen. People have a long plastic pipe and they roll it wherever they want and they lay down that pipe in their farms just to water the various parts of their farm actually. That is called a siphon. और a small PVC tube ले लीजिए, flexible one, उसको आप जब you can bend it in any जगह direction actually. So it is applicable in that particular part also, subsonic nozzles also, pressure drops also. So you can usually apply at that particular point. There your friction effects are negligible in that way. Constraints are these. Keep in mind the first four constraints: steady, incompressible, frictionless flow. These are the constraints. Let's see application where it is not applicable. First thing, as we say in the first beginning there, we were talking about Mach number, that gaseous flow and all this. And then we gave a question also in quiz and gave a wrong choice there, less than 1. So one of you were arguing that time, less than 1 could be any value. That's right. 0.99 is also less than 1. 0.98 is also less than 1. 0.5 is also less than 1. But exact answer is less than 0.3 actually. So gaseous flow can also be calculated or treated with Bernoulli. If your Mach number is coming less than 0.3, then you can treat that density variation is not much in that particular gases actually. Hydraulic pump, whatever pump you have, any pump, inside the pump you don't have any flow patterns because you are providing excessive energy to the fluid. You don't have a streamlined flow pattern in the pump. So Bernoulli is not applicable on the pump. You will have a pipeline. You have a pipeline here, just like a pan. Let's say this cap is a pump. So you can apply your Bernoulli from here to here, but not in this cap because this is a pump. Here you don't have a streamlined flow pattern. So you will always skip the pump actually. So inside the pump, Bernoulli is not applicable. So you can apply on a street pipeline, but not on the pumps. So hydraulic pumps are not applicable in Bernoulli actually. Second thing is not applicable on your propellers, your turbine, your wind. Anything where you have a rotation, your streamlined flow pattern is not there, you cannot apply Bernoulli. You have to leave that section as it is actually. You have to think what else can be done for that. Then again, airflow through a heating element, just like a hair dryer, something you cannot use that Bernoulli again because there also you don't have a flow pattern. Another means the constraint that where you have a deaccelerating flow, where you have the diffuser or divergence sections, sudden expansion or contraction, there also you don't get all these flow patterns. So you have to keep in mind where this Bernoulli equation can be applied. So these are some of the examples where you should skip your Bernoulli. Rest of the place you can apply actually. Fine. So I just told you the Bernoulli. There Bernoulli means the applications. Then you have here something about your flow meters. So Bernoulli application immediate use would be in there actually the flow meters there. So flow meters in that case you have a full bore meters. That I think I will complete in the next class because this will be a different part. What I have put here. I have to put something more here. Actually, there are several questions that need to be solved. So Bernoulli application derivations are there. Okay, next class we will do this part actually. Fine. So in this, we will end up the Bernoulli part there. That means use and Bernoulli and derivation and cylindrical coordinates also. So I will see that particular part. So anything you want to ask here till here actually whatever we did today.
सर इन ऑरिफिस मीटर सर वहाँ पे सडन कॉन्ट्रैक्शन नहीं होती क्या?
Sudden contraction in orifice meter, yeah, it is.
तो फिर सर वहाँ पे बर्नौली क्यों यूज करते हैं?
Yeah, that's what I told you. Use करने के we don't have any other option. How to calculate? So therefore, you are just putting a loss coefficient also there due to that the sudden contraction and all this. You are putting Bernoulli, fine. But at the same time, you are having a loss coefficient term. Therefore, your discharge coefficient, you are getting a discharge coefficient. Discharge coefficient in orifice is not 1, it's 0.61. So that is the losses only because of that sudden contraction losses. So to incorporate that, we did based on Bernoulli, but to incorporate the losses due to sudden contraction, so we have put a loss coefficient term there, and only because of that, you got a concept there, a discharge coefficient, and discharge coefficient for Bernoulli is only because of loss coefficient. Your pressure has been lost permanently. So 40% of pressure has been lost permanently. Therefore, your loss coefficient is not 1. In case of the orifice, it is the 0.61. Your 39% has went away. Okay, so you derived based on the Bernoulli taking the ideality, but it's not ideal, as you know, we also know. It is the sudden contraction which gave the losses actually, and to incorporate the losses, your loss coefficient in discharge coefficient in orifice is 0.61. Therefore, it's not preferred.
Okay.
Okay.
Yes.
So we will end up this class here actually. So tomorrow we will try to do this thing in the flow meter part here. Fine.
Thank you, sir.
Yeah. Bye.
Thank you, sir.
Yeah. Welcome.